Okay, so I guess you can hear me also now?
We can indeed.
Okay, perfect. Thanks. Thanks for the kind introduction. My name is Marvin, and I'm sitting here in this room together with Ragini. I'm going to present the Oldenburg team submissions to the second Clarity Enhancement Challenge, so submissions E36 and E38. The talk is going to be structured, as you can see on this slide here, where the main part concerns actually the two submitted systems. I will start by giving an overview of the structure that both of the systems use, since it's actually the same exact structure. I will then continue by explaining each of the systems in more detail, starting with the temporal convolutional network-based system, so TCN, and then continuing with the TCN-Conformer-based system, E36. After stating the training setup that we use to train these two systems, I will show you some simulation results and then finally conclude the talk. So since the motivation and design of this challenge have already been discussed before, I will jump right into the goal of our presented systems. So namely, in many situations, the binaural hearing aids do not capture only a target speaker. Or let me activate the laser pointer. But they can also capture some, wait a second. Okay, it doesn't want to activate the laser pointer, so I just leave it like this. They can also capture interfering sources such as noise or interfering music or also interfering speech. So the goal of our submitted systems is actually to get an estimate of the target speaker at the left and right ear. So because there can actually be an ambiguity problem, namely that the target speech extraction system doesn't know which of these speakers to extract, we actually try to use, or target speech extraction systems try to use this, to use auxiliary information to solve this ambiguity problem. As an example of such an auxiliary information, one can use an adaptation utterance, as you can see here. And basically, this is just an unrelated sentence spoken by the target speaker that is not contained in the mixture signals recorded by the hearing aid inputs. Okay, so now just as a reminder, we are presenting two systems here, which have exactly the same structure, and I will be representing the structure on this slide here. First, the encoder transforms the hearing aid inputs, namely the three on the left-hand side and the three on the right-hand side, into a binaural representation that is learned. And this, the goal of this representation is really to have information of the left and of the right mixture signals. Then, secondly, the extractor, it aims at estimating real valued weights that, when applied to this representation of the mixture signal, yield an estimate of the target signal, also in the learned representation here. Then the decoder takes this representation of the target speech signal estimate and constructs a time domain representation that the listener can actually listen to, resulting in this binaural speech estimate that you can see here. All right, so as the filter operation that we are utilizing here, we are utilizing a binaural weight and sum operation, as you can see here, which requires the estimation of 4 separate masks. So for example, in order to yield the estimate at the left ear, the speech estimate at the left ear, we apply one mask to the representation of the left mixture signal and also another mask or another weight to the right representation. And the same is also done in order to yield the right target speech estimate, as you can see here. And I want to also emphasize that all weights here are real valued and between -1 and 1. Now, in order to inform the extractor somehow which speaker to extract, we also make use of a so-called embedder. And the aim of this embedder is to take the adaptation utterance and map this adaptation utterance to a time invariant embedding of the speaker. So this doesn't have to be time invariant, but for our two systems, it is. And basically, this informs this extractor, okay, I want to extract the green source and not the red one. All right, so now let's get into the details of our TCN-based system, so using temporal convolutional networks. This is actually very similar to the time domain speaker beam, which has been proposed by Marc Delcroix and others. The encoder in this case consists of a single one-dimensional convolutional layer that you can see here, which takes as inputs all of the microphone channels, so channels 1 to 3. And then it yields a representation of the binaural mixture signal. As the extractor, we use TCN, followed by a prelude activation and a one-by-one convolutional layer to change the dimensionality. And afterwards, there's a tangent superbolicus activation in order to ensure weights between -1 and 1. Okay, so as the decoder, we are using here a one-dimensional convolutional transpose layer, resulting in this binaural target speech estimate. For the embedder, we are making use of a one-dimensional convolutional layer, like in the encoder, which yields a representation of the adaptation utterance. Afterwards, it goes into a much smaller TCN block compared to the extractor. And we perform temporal mean in order to yield a time invariant speaker embedding. Okay, so to briefly explain how we actually incorporate the information of the speaker embedding into our TCN network, so into the extractor, let's dive a bit more deeply into the architecture of this TCN that you can see here. Oh, sorry. So what is shown here is actually this TCN block in a bit more detailed view, this block here. Mainly, this TCN block consists of a number of TCN-conf blocks that have an increasing dilation rate, as you can see here. So starting with a dilation of 1 and then going up to 2 to the 7. The idea is here to increase the temporal receptive field of this architecture, of this TCN. And basically, this TCN has two paths where information can flow. The first path is marked in red here and is denoted as residual path. Basically, the goal here is to pass information between the different TCN-conf blocks. And then second, there's also a skip path marked in green, which is used to yield the output of this TCN block. Now, the method that we are using to inform the extractor of the embedding is the so-called film or feature-wise linear modulation method. And it can be seen here. So basically, you're putting these film layers between TCN-conf blocks. And the goal of this film method is to change the activations at each TCN-conf block. And how does it do it? By applying a scale gamma and a bias beta to these original activations A. And beta and gamma, so the scale and the bias, are obtained using one-by-one convolutional layers. So you can think of each of these film layers here being a one-by-one convolutional layer that takes as the input the time invariant speaker embedding. So in total, this enables the rescaling and biasing of the activations based on the speaker embedding E. All right, so now let's continue with the second system, which is based on a TCN-Conformer architecture that we've also used in a recent publication. For the encoder, we again make use of a one-dimensional convolutional layer, but it's actually two layers this time, which are separated into the left hearing aid inputs and into the right hearing aid inputs. For the extractor, we are making use of a number of TCN-Conformer blocks, as you can see here. And I will get to these blocks in a bit in the next slide. And for the decoder, we are making use again of a one-dimensional convolutional transpose layer. For the embedder here, we are using a ResNet architecture. And in total, this is very similar to the Specs Plus method. To inform the extractor of the speaker information here, we are making use of the concatenation method, which means that we just concatenate the speaker embedding along with the input to the individual TCN-Conformer blocks. And you can also see this here a bit more in detail. So this is, again, the TCN-Conformer in a bit more detail, starting here with the input signal. It's concatenated, as I just mentioned, along with the speaker embedding passed through a TCN-conf layer and a TCN-conf block. And then the output of this block is summed again with the input here and passed further to a conformer block. So this conformer architecture has been proposed by a team at Google for automatic speech recognition originally, where it has also yielded state-of-the-art performance. And the goal of this whole TCN-Conformer block is to utilize both the local modeling capability of the TCN and the global modeling capability of the conformer network, mainly motivated by the multi-head attention module that is contained inside of it. Okay, so because there has been quite a lot to digest with these two systems now, I want to quickly go through the differences of the systems again, with the TCN-Conformer-based system on the left-hand side and the TCN-based system on the right-hand side. For the encoder, we are using two one-dimensional convolutional layers separated between left and right for the TCN-Conformer. and a single one-dimensional convolution layer for the TCN. The extractors are based on TCN-Conformer or TCN, giving also the names. For the decoder, both methods use a one-dimensional convolutional transpose layer. And as the method of injection of the speaker embedding, in order to inform the extractor which speaker to extract, we are using the concatenation method for the TCN-Conformer and a feature-wise linear modulation or film method for the TCN network. Okay, so this is a depiction of how we trained these networks. In total, our final loss function consists of two terms, where the first term is a target speech extraction loss. So basically telling us how well has the target speech component been extracted from the mixer signal. And then the second part is a so-called speaker identification loss, which is used to basically make the speaker embedding that is obtained by the embedder more discriminative. Since for different speakers, the speaker embeddings should also look different. And for similar speakers or for the same speaker, these embeddings should look similar. In order to make use of the speaker ID loss, we require an additional classifier, which we have implemented using a linear layer that takes as the input the time invariant speaker embedding and then maps it to an estimate of the speaker ID. It should be noted here, however, that this linear layer is only required during training and not during inference. So in that case, we can just cut it off. Okay, so now let's continue with the simulation results, starting with the data set. We used the official challenge data sets for the training validation and also internal evaluation of our algorithms, which we have extended to a factor or by a factor of 10 using the official dataset generation recipe. So in total, this yielded 60,000 utterances for training, but we didn't make use of any external data or augmentation techniques. For the speaker embeddings, we just used random different utterances of the target speaker, since for the training set, there were no explicit mentionings of reference target speech. And as the input, we used the hearing aid inputs, so at the front, mid, and rear microphone, so channel 1 to channel 3, which means that we didn't make use of any head rotation signals or eardrum signals. And everything was downsampled to 16 kilohertz. So I just want to highlight a few more settings here. Starting with the frame length, which was chosen around 2 milliseconds and shift around 1 millisecond to abide by the challenge constraints of latency. For the target speech extraction loss, we used a scale invariant signal to distortion ratio for the TCN-Conformer, so a time domain loss function. And for the TCN, we used a so-called combined mean absolute error, which is a spectral loss function. For the speaker embedding loss, both systems use the constant entropy, and as the training target, the binaural reverberant target speech. We also experimented with using the anechoic speech. However, this actually yielded worse results in that case. And for the hearing loss compensation, we are making use of the baseline hearing aid processor. So our training was not including any individualization to the listener's characteristics. So here you can see the results of our internal objective evaluation, which is based on the 500 last development dataset scenes, which were of course not used in the validation of our algorithms. You can see the results in terms of the individualized Husky scores as also done in the official evaluation. And you can see the results here on the right-hand side. I hope you can see it. So on my screen, you should be able to see it. So here we see the mixture and the baseline, and then our two submitted systems, namely E36, the TCN-Conformer-based network, and E38, the TCN-based network. And you can see that both systems achieve significant improvements compared with the baseline system. And also that the TCN-Conformer network significantly outperforms the TCN-based network. Furthermore, if you look at the distributions of the Husky scores here, you can see they look quite different. Namely, for E38, we seem to have more weight around the extreme values, so high values and low values. While for E36, we seem to have more weight around the mean value. And we were very interested in what the influence on the subjective evaluation could be. So this is actually why we submitted both of these systems. And as we could see from the preliminary results, the performance of E36 was higher than for E38, also subjectively. Okay, so here are just some audio examples that I want to play. starting from the left and then going to the right. I hope you can hear them.
There is no provision for one in the bill. There is no provision for one in the bill. There is no provision for one in the bill. There is no provision for one in the bill.
Traditionally, cod, haddock or flounder are used to make fish and chips. It's 15 degrees with a...
We at least went to the trouble of asking them. We at least went to the trouble of asking them. We at least went to the trouble of asking them.
So I think you might have heard that there are quite some noticeable perceptual differences between the two systems. Yeah, again, one of our motivational parts for submitting two systems. All right, to finally conclude the talk, we presented two TCN-Conformer based and TCN-based target speech extraction systems, which were individualized using the baseline hearing aid processor. And both systems achieve considerable objective intelligibility improvements, outperforming the baseline system, where the TCN-Conformer-based system yielded higher improvements than the TCN-based one. The distributions of the Husky scores were quite different. And that's it. So thank you a lot for your attention, and I'm open to any questions, along with Ragini also.
Thank you, Marvin, for an excellent talk. Thank you very much. While I wait for questions to come in from the chat, Brian Moore, my apologies for missing your hand up earlier from the first talk. If you could type your question into the chat, then we'll endeavour to answer it. And I'm just seeing that John Barker has his, John, you have your hand up.
Oh yeah, thanks, Marvin. That's really interesting work. Well, I was interested in the training data. So you said you extended the training data to something like 60,000 scenes, but you did that kind of using the kind of official remixing data. But did you also evaluate using just the 6,000? Because I was kind of interested to see how much gain you got from that extension. Did you look at that?
Yes, we also trained using only 6,000 utterances, and it seemed that at least with our training setup that we used, we achieved slightly higher improvement using the extended data set. So it was a significant difference, I would say, but it wasn't anything crucial. So not like 50% improvement over that.
Okay. Another quick question I had was the speaker embedding. Was that kind of based on external data, or did you just train it on?
Exactly, it was not using any external data. It was just using the official generation. So basically, we just took the training set, and we extracted the utterances that belonged to the specific target speaker that was present in the mixture, and then we used this one, or actually we chose randomly from these utterances in order to yield the reference utterance. So it was just using the official data.
Because there weren't that many speakers in the training set, so I was wondering, kind of, you had a better embedding, like using Celeb or something. You know, whether how much improvement that would.
Would be very interesting to investigate. But we actually just made use of the very limited number of speakers that were present, and probably this also might have had an influence on the performance of these embeddings.
Yeah, I expect so. Okay, no, thank you.
Thanks for the question.
Thank you very much, John. Marvin, I'll ask the same two questions of you that I asked of Zahai, if I may. What did you find particularly challenging, and what of your solutions are you most proud of?
Yeah, so very challenging, I think, were these very low SNR scenarios. So I think we were at sometimes surprised by how little you can hear of the target speaker, at least in some scenarios. It's actually difficult to guess if there even is a target speaker. And yeah, this was very interesting for us to see. A bit unfortunate was the performance of these systems, especially in these low SNR scenarios, I would say. But I think what I was most proud of was, actually the collaboration along with the colleagues, which led to many interesting discussions. And also, because of such a challenge, you are kind of forced to work together. And I'm very proud of of this working together, of this collaboration, I would say. Even though the results in the end might not have been as good as they could have been, but that's okay.
Well, thank you very much for your talk and for the advances that you've made. Thank you.
Thanks for having us also.